Why time stops. At the speed of light, the hidden structure of the universe. Deep beneath the border between France and Switzerland, protons race through a circular tunnel 27 kilometers around. This is the Large Hadron Collider, and these protons are moving at 99.99999% the speed of light. Engineers have poured enormous amounts of energy into accelerating them. Powerful magnets bend their paths. Detectors track their every movement. But here's something strange. No matter how much more energy you add, the protons never quite reach the speed of light. They get closer. More nines appear after the decimal point, but they never cross that final threshold. It's not a limitation of our technology. It's not that we need better magnets or more powerful accelerators. The protons can't reach light speed because the universe won't allow it. The closer they get, the more energy is required to push them even slightly faster. The energy required to actually reach light speed would be infinite. And if a proton could somehow reach that speed, something even stranger would happen. Time would stop, not slow down. Stop. The proton would traverse the entire 27-kilometer ring in zero proper time. From its own frame of reference, if such a thing existed, no time would pass at all. This isn't science fiction. This is special relativity. And the reason massive objects can't reach light speed, the reason time behaves differently at different velocities, comes down to a single shocking fact about the universe. The speed of light is the same for everyone, no matter how fast they're moving. And once you accept that fact, everything else follows. Let's see why. Invariant C. In everyday experience, velocities add in a straightforward way. You're on a train moving at 50 kilometers per hour. You walk forward at 5 kilometers per hour relative to the train. From the perspective of someone standing on the platform, you're moving at 55 kilometers per hour. Your velocity plus the train's velocity equals your total velocity relative to the ground. This is classical velocity addition. It's intuitive. It matches our experience. And for ordinary speeds, it's an excellent approximation. But it's not exactly correct. In the late 1800s, physicists began studying light. They performed experiments to measure its speed, and they discovered something deeply puzzling. Light always traveled at the same speed, regardless of the motion of the source or the observer. About 300,000 kilometers per second, usually denoted by the letter c. If you're standing still and measure the speed of light from a lamp, you get c. If you're moving toward the lamp at half the speed of light and measure again, you still get c. Not 1.5 times c, just c. This violated every intuition about how motion works. It suggested that classical velocity addition was wrong, at least when light was involved. Albert Einstein took this seriously. In 1905, he published a paper proposing that the speed of light is genuinely invariant. It's the same in all inertial reference frames, regardless of how those frames are moving relative to each other. This wasn't a property of light specifically. It was a property of spacetime itself. Light just happened to travel at this fundamental speed because photons have no mass. But accepting this invariance has profound consequences. If the speed of light is the same for everyone, then something else must change. Time and space themselves must be flexible. Here's why. Imagine two observers. One is stationary, standing on a platform. The other is on a train moving past the platform at constant velocity. A light beam is emitted from the front of the train toward the back. From the perspective of the person on the train, the light travels the length of the train car at speed c. Simple. The time it takes is the length of the car divided by c. But from the perspective of the person on the platform, the light has to travel further. While the light is moving from front to back, the back of the train is moving forward. The light has to cover both the length of the car and the distance the train moved during that time. In classical physics, you'd expect the light to take longer to reach the back of the train, as measured by the platform observer, because it's covering more distance. But the speed of light must still be c, the same c for both observers. The only way this works is if time itself runs at different rates for the two observers. Time on the moving train must run slower, from the perspective of the platform observer, so that the light still travels at c, despite covering a longer path. This is time dilation. And it's not an optical illusion or a measurement error. It's a real difference in how time flows. Time dilation. Let's build an intuition for time dilation using a thought experiment. Imagine a simple clock. It consists of two mirrors facing each other with a single photon bouncing back and forth between them. Each round trip of the photon from one mirror to the other and back counts as one tick of the clock. If the mirrors are 1 meter apart and light travels at 300,000 kilometers per second, then each tick takes about 6.7 nanoseconds. This is a light clock, and it's a perfectly valid way to measure time. Now put this clock on a train moving at high speed relative to a platform. From the perspective of someone on the train, the clock works exactly as before. The photon bounces straight up and down between the mirrors. Each tick takes the same amount of time. But from the perspective of someone standing on the platform watching the train pass, the photon's path is different. The photon doesn't just go up and down. It also moves sideways, because the entire clock is moving sideways with the train. The photon traces out a zigzag path, up and to the right, down and to the right. The distance the photon travels in one tick, as measured by the platform observer, is longer than the simple up and down distance measured by the train observer. But both observers must measure the photon moving at the same speed, c. That's the invariance of light speed. The photon can't go faster just because the platform observer sees it traveling a longer path. The only way to reconcile this is if the tick on the moving clock takes longer, as measured by the platform observer. The train clock runs slow compared to the platform clock. This isn't specific to light clocks. All physical processes on the moving train run slow from the platform's perspective. Chemical reactions, biological aging, atomic vibrations. Time itself is dilated. The amount of dilation depends on the velocity. At everyday speeds, the effect is tiny, imperceptible. But as you approach the speed of light, the dilation becomes extreme. At 90% of light speed, time on the moving object runs at about 43% the rate of stationary time. At 99%, it's about 14%. At 99.99999%, like the protons in the Large Hadron Collider, time runs thousands of times slower. And at the speed of light itself, time stops entirely. The dilation factor becomes infinite. Zero proper time passes along a light-like path. Length contraction. Time dilation isn't the only consequence of invariant light speed. Space contracts too. From the perspective of the moving train, the platform appears length contracted along the direction of motion. Distances shrink. The platform observer measures the train as a certain length, but from the train's perspective, the platform is compressed, shorter than it measures itself to be. This is reciprocal. Each observer sees the other's lengths contracted. There's no absolute reference frame, no privileged perspective. Length contraction and time dilation work together to keep the speed of light constant in all frames. When you move relative to something, distances in the direction of motion shrink, and time for the moving object dilates. These two effects combine in exactly the right way to ensure light always travels at sea. Imagine you're on a very fast spaceship approaching a star. You measure the distance to the star as shorter than it would be measured by someone at rest relative to the star. This is length contraction. Your journey to the star takes less time on your clock because the distance is shorter. But from the star's perspective, your clock is running slow due to time dilation, which explains why you age less during the trip. Both perspectives are consistent. Both give the same answer for the speed of light. The geometry of spacetime ensures it. This is why relativity is ultimately about geometry, not about light being special. Light travels at c because c is a fundamental property of spacetime geometry. It's the conversion factor between space and time. It's the maximum speed at which causality can propagate. Objects with mass can't reach this speed because the geometry forbids it. Why mass can't reach key? Let's think about what happens when you try to accelerate an object. In classical physics, if you apply a constant force to an object, it accelerates at a constant rate. Its velocity increases linearly with time. Keep pushing, and it will eventually exceed any speed you choose. But in relativity, this doesn't happen. As an object's velocity increases, its momentum increases faster than classically expected. The relationship between force, momentum, and velocity changes. There's a factor, usually called gamma, that appears in the equations. Gamma depends on velocity. At low speeds, it's approximately 1. At half the speed of light, it's about 1.15. At 90% of light speed, it's about 2.3. At 99%, it's about 7. As you approach the speed of light, gamma approaches infinity. Momentum is proportional to gamma, so as velocity increases towards c, momentum grows without bound. Adding more velocity requires adding more and more momentum for smaller and smaller gains in speed. Energy is also proportional to gamma. The total energy of a moving object includes its rest mass energy, the famous E equals mc squared, plus its kinetic energy. As velocity approaches c, the total energy approaches infinity. To actually reach light speed would require infinite energy. The universe doesn't have infinite energy to give, so massive objects asymptotically approach light speed but never reach it. This is why particle accelerators can't push protons all the way to c. You can get extraordinarily close. You can pump in more and more energy. But each increment of speed costs more than the last. The curve never quite reaches the limit. Light itself, photons, can travel at c because they have no rest mass. They don't need to be accelerated from rest to light speed. They always travel at c. It's their natural state. In fact, they can't travel at any other speed. But anything with mass is locked below that threshold, not by technology, not by engineering limits, by the fundamental structure of space-time itself. What time stops really means. You'll sometimes hear that time stops for a photon, that from a photon's perspective, it travels from one side of the universe to the other in an instant. This needs careful interpretation. Mathematically, the proper time along a light-like path is 0. Proper time is the time measured by a clock traveling along that path. For an object moving slower than light, proper time advances normally. For a photon, proper time doesn't advance at all. But this doesn't mean photons have a perspective or experience time the way we do. It's not that a photon sees the universe frozen. It's not that a photon has subjective experiences. The phrase, "from a photon's point of view," is a metaphor, and it's a misleading one. There is no rest frame for a photon. You can't boost into a reference frame moving at the speed of light. The mathematics breaks down. Gamma becomes infinite. What we can say precisely is this. If you could travel at light speed, the space-time interval along your path would be 0. The combination of time elapsed and distance traveled, weighted by the geometry of space-time, would vanish. Your departure and arrival would be the same event from your own frame of reference, if such a frame existed. But you can't travel at light speed if you have mass. So this is a limiting case, a boundary condition that objects with mass approach, but never reach. For practical purposes, light propagates instantaneously along its own world line. It connects distant events with 0 proper time. This is what we mean when we say time stops at the speed of light. It's a statement about geometry, about the structure of space-time, not about consciousness or experience. The invariance of light speed has one more profound implication. It defines causality. Cause and effect can't propagate faster than c. If an event happens here and now, it can only influence another event if that event lies within the future light cone. The region of space-time that light could reach, traveling outward from here and now. Events outside the light cone are causally disconnected. They can't affect each other. There's no signal, no force, no influence that can travel faster than light. This is why C is special. It's not because light is magical. It's because C is the speed at which causality propagates through spacetime. Light happens to travel at this speed because photons are massless. But even if light didn't exist, C would still be fundamental. It's woven into the geometry of spacetime itself. It's the conversion factor that makes time and space compatible, that lets us treat them as dimensions of a unified four-dimensional structure. Time dilation, length contraction, the impossibility of reaching light speed. These are all consequences of living in a spacetime with this structure. A spacetime where C is invariant. And the stopping of time at light speed is just the limiting behavior of this geometry. The point where motion through space completely replaces motion through time, where the world line becomes null, light-like, zero proper time. We can't experience this directly because we have mass. We're confined to time-like world lines, always moving slower than light, always experiencing the flow of proper time. But light, or more precisely, anything traveling at C, lives on the boundary, the edge of causality, the speed at which information, influence, and cause and effect propagate through the universe. So here's the question I'll leave you with. If the speed of light defines causality, if it's the maximum speed at which information can travel, then what does that imply about simultaneity? If two events happen at different locations, is there an absolute answer to whether they happened at the same time? Or does that depend on your reference frame? Think about that. The universe has a hidden structure, and once you see it, you can't unsee it.